A lot of times we think of handicap design for the handicapped as like this extra thing that needs to happen. That awkward aluminum ramp up the side of the house, or janitor's closets have been turned into a handicap toilet or something. And I was really impressed. I saw a photograph of and some plans of restrooms at Gallaudet College in DC, which is a school for the deaf. And they said, nah, everything we do from now on is going to be completely universal design, so that nobody has to feel like they're being treated as second class or have to go around to the back or yada, yada, yada. And by the time you bring in people who are blind as well as deaf, some of them are in wheelchairs, some of them are transgender in different directions. They decided we can't make like 9 different bathrooms. I mean, transgender men in wheelchairs, like that. So what they did is where the restrooms used to be, there's this lovely lounge, Wi-Fi and everything, and just a series of restrooms, each of which has a sink, a toilet, a urinal, and a changing station. And you just wait till one says available and you go in and use it. It's not space efficient, but it's certainly welcoming. And to me, that's sort of the most clear example of universal design that I've seen. Okay, so I think in this course, where the mouse meets the screen, we're actually going to be drawing stuff. Mostly we'll be dealing with all the issues of accessible routes and of plumbing elements and facilities. Those are sort of the names of those in the ADA book. An accessible route is everything from the bus stop to the bathroom and the dean's office. It's talking about curb cuts. It's talking about the angles of a curb cut, so you can get a wheelchair up it or on your crutches when you break your leg or something or other. Which brings up something else. Wheelchairs represent sort of the most extreme case of what we need to accommodate. But imagine a supervisor in an auto parts plant where you wouldn't be thinking about handicapped access. And he broke his leg skiing, but he's going to be on crutches for a month, and he needs to get everywhere to see what people are working on. He needs to be able to use the bathroom. So it's not like this is just for customers or students. This is for everybody employed and going everywhere, using anything that they need for their job. So it really is beyond getting wheelchair people into the building. It's the whole thing from the curb to the restroom and everywhere in between, up and down, anywhere that people have a need to get to. Not mechanical rooms, not up ship's ladders into the attic, but the rest of it. General background, I just want to throw this in because it'll keep coming up as we're going through the different codes. There are a lot of ways to describe a building. One is, how is it built? What is it made out of? From a fire safety standpoint, how combustible is it? I think Schneider Hall is a type 3 because although it's low and made out of concrete, it doesn't have sprinklers. At the combustible end of the spectrum might be a residential garage that's just built out of studs and plywood. So what things are made out of affects what has to happen in them in terms of sprinklering and egress and that kind of stuff. So how they're built, what their purpose is. Clearly, you need a different set of doors for an auditorium than you need for what's another big room? A lab, for instance. Just many more people in the dark versus a lab, which presumably has relatively able-bodied people and not that many of them. There's a couple of different kinds of assemblies. So an A1 assembly, I'm not going to go into great detail, but that would be for auditoriums where there might be a need for people to get out quickly, let's say, when they've been in the dark. Food and drink, they might not be so densely packed, but they might be drunk. This happens at restaurants, and people need to leave and not trip over themselves. And then other A3 is like where people are more or less not too tightly packed, but are presumably awake and there's lights on. And there are a couple others, but that's the idea. And some of those occupancy groups need different kinds of routes to get into them and to get out of them. For now, I'll be mostly addressing accessibility, just being able to get to stuff. But this whole time, a lot of these routes will also be used for emergency egress. And that's where the egress calculations come in, which is how wide do the doors have to be? How wide do the hallways have to be? How many doors? How many halls? How far apart? What direction do they go? That kind of stuff. And I want to address that theoretically in about 2 weeks. I'll have to study up on it because I haven't been responsible for planning it for a while. So we're starting with ramps, what's involved with them, and then moving on to stairs. I'm going to skip handrails and guardrails. There's a lot there that I want to do as part of the talk where I address complex assemblies, which are them and storefronts and something or other else. I forget which. I'm getting my stove. And then a big part of all this is clearances at doors. Depending on which direction you're coming at a door, especially in a wheelchair, which is worst case, you need to either get next to it and be able to reach it and pull it open and go in, or can you just push it and go in, or does it have a closer and stuff? And so I've put together, as you can see here on page 3, This combines the 6 most common ways to approach a door and shows you graphically the clearance you need that can't have sinks or walls or columns or stuff like that in it. Elevators are pretty easy. Basically, we're just given a rectangle we need to accommodate. And the ones that come with Revit we can adjust the width and the depth to fit the space we have. Plumbing fixtures. This was the tough one. This is 2 pages to find out what we need to do on this floor for restrooms. This is the one where we're going to have to start dealing with 3 different documents, the building code, ADA, and the Kentucky Plumbing Code, to understand what's required and what we need to provide, which we're not providing. And through all these, the codes are assuming, which they really have to do, is worst case. And the worst case for determining everything about this building is if every classroom was full at 10 o'clock in the morning to its maximum capacity, and everybody had to leave at once, or everybody needed to use the restrooms during a class break. So it's different from what goes on in a business where presumably the bathroom use is even through the day. Here we have these hourly spikes in demand. I tried in each of these cases to pull together the important design considerations that we need to go through for each of these. They're not always in one book in this order, but it's like, what all do we need to know to be able to, for space planning purposes, so we know we've got enough room for a given stair or ramp, and then when we come back, we can fine tune handrails or landing slopes or something like that. First of all, what is a ramp? Good. A ramp is a ramp. If the slope is less than 1 unit up for every 20 this way, it doesn't count as a ramp. An ADA compliant ramp is one whose slope is from 1 to 20 up to 1 to 12. These are horizontal and vertical dimensions, not along the slope. So anything in here, that's what we're dealing with. And then anything over 1 and 12 is verboten, can't do it. Can't do it in accessible design. At a loading dock somewhere, they need to put in a ramp to get hand trucks up, and all they have room is for something that's steeper than that. Fine, do it. It won't be being used by people in wheelchairs or whatever. That's not part of the required accessible route into and out of the building. Similarly, you can certainly have as much of this as you want on a site, and you can put handrails on it if you want. For the past 20 or 30 years, I've been working on various projects at a residential school for mentally handicapped adults, some of whom have other mobility and balance issues. Lately, we've been adding handrails to walkways considerably less steep than 1 and 12. And most of the times we do it on 2 sides, even if it's like 8 feet wide. And that seemed like extra money. And I asked about it and said, well, we don't know which hand works. You know, if you're going up the hill and this is the hand that works and there's no handrail there, because it's over there, that's not going to work. Can't back up. So that was instructive to me to start thinking about, oh, yeah, this is more multidimensional than I'd thought about. Ramps got to have handrails, and usually those are 2 parts where the guardrail is what actually keeps you from falling off. And that's usually 42 inches high. And then the handrail is what you grip that's down below that, so you can pull yourself up the hill. Or ramps need to have a level landing at least every 30 inches of vertical rise. And if we're assuming that we're working at 1 and 12, that 30 inches here, we're doing 30 feet here. And then we need at least a 5-foot landing and then another ramp. And then whatever happens at the top and the bottom. And at the top of the bottom, we also need 5 feet just to come off level and get situated and turn around. You can't just come off it and then hit something. You got to have a place that doesn't have doors swinging into it or columns or anything like that. So that's also 5 feet over here at the top. And that might be part of the floor. It might be structurally part of the landing. It just depends on what that particular configuration is. But these get really pretty long. If we want to go up, let's say we want to go up 5 feet, 30 feet there, 30 feet there. The whole thing is 65, 70, 75 feet long to get up just 5 feet. So it's a chunk of space. Easy to do outside, hard to do inside in an existing building. Interesting to do in new construction. We're starting to really think about it. Let's just look at those. The tool here is ramp, architecture ramp. And as we're building that, as we're creating this, property starts determining what this kind of ramp is going to be like. And the first thing we do is how high does it need to go from landing to landing. It always defaults back to level 1 and level 2. So if you just want to go from level 1 up a little bit from there every darn time, you need to come back and change it to level 1 And let's say we're going up, I'm going up 6 feet. So 6 feet is 72 inches. We know we can do 30 inches per run. So we know we're going to have to have at least 3 different runs, 30 maximum, and 12 off at the end. Or we could do 324s, or we could do 418s. You can just do that, whatever your geometry and if you want to like go around a space, I mean, with the tree in the middle, that could be 3. If you want it zigzag, that could be 4 or 8, any number like that. At some point, the landings just financially start becoming this big amount of it. And I think generally we want to sort of play them back down. But let's say we're going to let me do the 30-inch one, 30 and 12 first, because Revit does that all by itself. In edit type, it says, what's the maximum length of incline? And it's just going to stop there at 30. And then we are prompted to start a new run. But so this ramp 2 type, I'm going to rename it to be 30-inch rise, just to remember how this is working. So since we made that change, ramp 30-inch rise, going 6 feet, I'm just going to start here and start drawing. As we zoom in, I have to click to say where I want that to stop. It'll stop at 30 feet. And then the next click will be the end of the landing and the start of the new run. So we're just doing point, 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 point. 1, 2, 3, 4, 5, and 6. And for right now, I'm just going to eyeball 5 feet. I think right now it's 3 feet wide, as we can see here. I'm just going to go over here somewhere. And then here comes my next run, which I can aim in any direction I want. But I'm just going to keep it going straight for now. Click, start my next one, and it'll put in the 12-foot one. And I'm just going to say, okay, close enough, good enough for government work. So it'll turn that sketch into a 3D ramp with a railing on it. And for right now, I'm going to erase the railings because they are just in the way and I don't want to deal with them yet. So I can just pick the railing, hit delete. It's easy to put them back on. So there's that. Right now, it's hard to tell that that's any different from essentially level. We're just sort of crooked. But if we go to edit type here, select it and go to edit type, we can change its shape from thick, which means like a thick slab, to a solid that goes all the way down to the ground like a big exterior concrete ramp. So now you get to start to understand what that's all going. Okay, so my boss says, Bill, I want to spend as little money on this as possible. Are you sure those landings are only 5 feet long? Make sure they're 5, but don't go over 5. So I'm going to just put dimensions on here. Annotate dimensions. And there's our 30. Oh, I spent 5 inches too much. So fortunately, because all 3-dimensional objects in Revit are created from 2-dimensional ones, all we have to do to change the 3-dimensional one is to modify the 2-dimensional one to be what we want. So if we select the ramp and go to edit sketch, and now we're just dealing with lines. And we'll start dealing with stairs the same way, where they have a green boundary that runs down the edge, and then the black risers where either the step happens or the landing starts. So this is fine. If I want to move this guy in to where that's 5 feet, I can select it. And then down here, say instead of 5.5, I just say 5 feet. And then that moves down to be 5 feet. In all of these, to change the location of something or the size of something by using its dimension, which is a wonderful tool, you don't pick the dimension, you pick the thing, because that's what you're modifying. And then the temporary dimension shows up and you change the dimension there. So if I want to pick this guy, so since that moved down some amount, I want to move this down some amount. So I pick that line and it says 30 feet. I'm just going to make it 30. we're still good. And then to move this guy, I make him be 5 feet. And then move this guy, so he's 12 feet. Let's hit OK and see if it works. Et voila! These all take some practice. So there's a straight ramp that goes up 6 feet. If we wanted one that had even 24-foot sections, we could create it from scratch, or we could just take this one and move the landings. Just as I moved them before, move them so I have 3 equal 24-foot runs. And sometimes it helps me in a plan view is just with lines or detail lines, just to sketch what I want to have happen and be able to play with it just on the level of lines and spaces and being offsetting 5 feet for the landings rather than having to deal with the whole 3-dimensionality of it all the time. And frankly, once I often build my stairs and ramps outside the building shell just so I can see it and make sure it's right, and then I just move it into place with a corner or something. So how about an L-shaped ramp? Let's make it 4'6". So we'll do a 30-foot one here for 30 inches and a 24-foot one for 24 inches. And this will be the landing. Here's how you do that. Architecture, ramp. I got to go back and change these. I don't want going 6 feet above level 2. So it changes back to level 1. Make this 4'6" so I don't have to do too many landings. L-shaped one, 30. And then remember, the next point I pick is the beginning of the next run of the ramp, and Revit will create the landing. If I want the next run to start right there, I'll do that. Or if I want to make the landing be longer this way, I'll go like this and then start it down here, let's say. And Revit will put in the L-shaped landing. Once you absorb how it works, it's a pretty clean process. Stairs, if you're working inside a room, do you want the points that we pick to be down the middle of the staircase or over against the wall and into the corner? Ramps don't have that. It's just always right up the middle. And we can always adjust it to suit. And when I say adjust to suit, it's like we can now edit this. If we're, it should have been 48 inches wide, or I don't have that much room for a landing. You can always come back to a ramp, and let me get rid of these railings just so we see the thing itself. We can select the ramp and go to Edit Sketch, and now we're back just dealing with the lines again. So if I want a smaller L-shaped landing, I can move this down, move this back. L-shaped landing. Well, Control Z. I'd have to think about that. We can stretch these out to make them wider. Line is too short. Controls cancel. Line is too short. Cancel. That was some little line. Oh, I'd shortened that line up too small. In which case I can get rid of it and drag this one over to here, and then slide this to be to there. Revit won't check to see if this is a valid ramp until you finish editing, so you can play with the lines themselves to your heart's content. So we can play with these once they're approximately in place. We can tweak them to fit the space available. What else we have? Well, let's do one that has. I'll try to do one that's just like this, where this one ends, this one starts with a gap in between ramp. Back to level 1. Go there. And then to start in line to go up this way, I'll wait till I get that blue alignment arrow going. Click and click. And if I wanted them to be equal, Yeah, shortened it too much, but you can play with them that way to make them work. The architectural project template comes with two ramps, ramp 1 and ramp 2. They're identical to start with. And for some reason, ramp 2 is the one I picked, and I renamed it. If I go into edit type, we have the choice between solid and thick. And thick is just a slab. So if I change that ramp type to thick instead of solid, we can also set how thick it is. Let's say 8 inches. Apply. Okay. So that those all become 8-inch slabs, which I'm not going to keep because I want to see the thickness of them. You'll be glad to know that stairs work much the same way. We define runs of stairs and landings and another run of landings. A couple of things to bear in mind as we're dealing with accessible design is the minimum riser height tread to tread is 4 inches. And the one out in the circular one out here is pretty shallow, it seems to me. I mean, it might just be like 6 inches or something. 7 is more standard. That's also the maximum. And you can't have open risers. It's got to be a solid, something that people's toe would meet. You know, it looks awfully nice, that staircase, but imagine the situation of somebody on crutches is going up there with his cast or her cast, and their foot goes past the riser and they fall backwards and their foot breaks off. I mean, that's why risers are closed. Your toes hit something before they go through and imperil you. Just so you know. Also, the ADA standards come from the Justice Department. It's not like transportation. It's not like health, education, and welfare. It's the Justice Department. And this is the Attorney General of the United States and his minions on down the line who are charged with enforcing this stuff. Even presidents and ex-presidents get in trouble with the Justice Department. So you know, be good, children. Okay, enough of that. Stairs. Minimum tread depth is 11 inches for accessible. And the minimum number of risers in the run is 2. It's really disconcerting to be, this is a section view, just to have that happen. Even if there's, you know, a handrail on the wall, nobody sees it, nobody pays attention. Got to have at least 2 and an appropriate handrail for that whole thing. And the handrail is as much to call attention to it as to actually support people who need it. Step coming up. Minimum number of risers in a run of stairs is 2. And the maximum rise of any single run of stairs between landings is 12 feet. That chart is from the International Building Code. Let's just make a simple staircase going up from level 1 to level 2, which is 10 feet, so it can be a straight run if we want it to be, because 12 feet is our maximum. Just go to stair. And we have 2 types come with the program. This assembled stair, which is, you know, treads and risers and stringers and stuff, or monolithic, which is like cast in place concrete, one big solid lump. And let's look at that one first, because it's clear what's going on without dealing with all the parts yet. So let's say a monolithic stair going from level 1 to level 2. Fine. We can draw it in 3D just as well as we can draw it in plan. The blue line will snap in when we're at a 90-degree. Well, let's see, we'll do it down there. Yeah, when you're at 90 degrees, so you don't have to fake it here. So we're seeing 18 risers created, 0 remaining. Looks good to me. Okay. And again, I'll get rid of these. So if we look at this in a front view, can I do that? Let's move that over there. Let's put a couple of dimensions on that just to see what we're dealing with. Make sure Revit did what it was told. You can't dimension. This is really a 3D view that happens to be looking at the staircase from the front. It's different from a true elevation view. This one I can just, if I want, start doing that too, which you can imagine would make dimensions just go nuts. So let's just come into the south elevation view. This is a true view where we can do what we need. Why isn't that working? In the middle of the command. What? Huh. Why did that do it? Oh, it didn't do it because I clicked on the little button, not on the word. Let's go back to south. That's where I know what I'm doing. Okay, now in an elevation view, I can dimension this. Aligned might pick up like the angle here because that's an aligned edge. So I'm going to use the linear tool, which will only give me horizontal and vertical ones. For reasons unknown, it's just not picking these up. I'll try something else. I'm not sure why it's not picking up the edges right now, but as with many things in Revit, when you are hovering over a point, you can hit Tab a couple of times until the different object, oh, there we go, until the different things that it could select there are actually selected. Well, let me go from endpoint to endpoint. And then again, with this linear dimension tool, if you drag it up, it gives you the horizontal dimension. And if you drag it sideways, it gives the sideways dimension, vertical dimension, I should say. I'm going to change my scale from 1/8 to, let's say a half inch equals a foot, just so my text will be smaller. So that's the riser height. And then the treaded depth is from one nosing to the next nosing horizontally, and every one of the codes will say the exact same thing. So we'll go to linear. You have to tab till you get a point, tab till you get a point, and then drag it up. A 1 foot tread depth is greater than I need. I only need 11 inches. Generally, we're trying to keep these as small as possible within the code so we don't have to pay the extra money or take up the extra space. So let's see why that did that. If I select the staircase, go to edit type, I can see, oh, that's because that type wants to be a foot. So I make that 11 inches. Apply. Okay. We changed the minimum width to 11 inches, and this is 12 inches, so it's still okay. Let's go back to do another stair right next to this one to see architecture, stair, cast in place monolithic stair. And we can see that now it's set for an 11-inch tread. Minimum tread depth, okay. Now I'm just going to start right here, and we'll get that far. And okay. So we picked up 1.5 feet because we got rid of 1 inch times 18. So we're that much shorter. So the riser height will be the same. And the ending height will be the same, but the tread length will have changed from 12 to 11. So let's say that for some reason we would like to add a landing. What's the procedure? So we'll go with this same stair type, and we go to stair, architecture stair. It will remember our previous settings. But actually, it would always default back to level 2, but in that case, this is what we want to use. So knowing that I have 18 treads, I can click here and go to where 9 are created. 9 risers created, 9 remaining. Click there. Come over here a ways, whatever I like, to start the next run. And take the rest of them. And I can drag this out past if I want to, it doesn't matter. And we see that Revit has put in the landing from where those 2 points, point 1 and 2, point 3 and 4. Run and run. So there's that guy. And you can figure out how to do the other stair and landing combinations. Let's look at some of the options that we have with stairs. One would be to change this guy back to the built stair, basically wood treads with risers underneath. We'll change it from being a monolithic stair to being the one, the assembled stair made out of parts. And at this point, these could be anything. We haven't yet determined a material for that. In an office building, that would be a steel channel running up there and holding steel treads. In a house, that might be a 2x12 with the wood treads in between it. But we have a couple of choices of placement for this. Let me put a wall here. Where are we? This guy, I guess. Just to show you some of our options. So if that's against a wall, in a residence typically, and this is freestanding, so you can see we're going up. These are called a closed carriage, where the ends of the steps are blocked off by the stringer. If we decide we want, let's say, this side to be tucked in underneath it, we're going to edit the type. So this will apply to all the stairs that we put together like this. So we might really want to rename this one to be, or duplicate it, rename it to be assembled stair, right stringer underneath or something. But let's just look at what's possible with it. I'm going to edit type. I want to say that the right support, which is the one out here towards the room, I want that to be open. So that tucks in underneath. And the other one, I want to be not 2 inches thick, but just a 3/4 inch piece of 1x12 that slides in there and receives those. So again, we can go to here, edit type, and say that the left support, this is always as you're going up, the left support is going to be closed, but I want it to be, we're going to have to duplicate this and make a 3/4 inch stringer, just with edit type duplicate. Okay. And then we actually change the width of that stringer to 3/4. See if I'm doing this right. Okay. Okay. Good. And then that shrank down to be 3/4 inch standard trim material instead of a big fat construction 2x4. At that point, I'll need to move this whole thing back against the wall, but you can see what the effect of that is. And lastly, with this run type, you can see we've got not only a tread, and the treads are rectangles, but a nosing has been applied to this, and we can choose the shape of the nosing. And there's just a couple built in, this one and like a half round. And we can choose which edges those go on. So, this is like this is like before they put the trim on. I want to basically add that nosing around to the right side of the tread to hide the end grain. So it'll be a miracle if I get through this whole thing doing it right. So run, and there's a 1 inch nosing. Okay, that's good. It's in there somewhere. So we can say apply the nosing profile, not just to the front, but to the front and the right. That should wrap around just on this exposed side. And I'm going to make the riser thickness 3/4 inch, because that's what it would be with wood. 1/4 inch is like for metal. And instead of extending the riser coming down behind the tread, I'm going to have the tread go underneath the riser. Extend a tread under a riser. Okay, apply. Okay, apply. Okay. So just with the blink of an eye, potentially a whole building's worth of staircases that are all of this type had our carriage is inset, our nosing extends around this exposed side, and this has changed from being a 1/4 inch piece of metal to a 3/4 inch piece of wood. I would suggest when you are just laying out your stairs, not even to think about this level of detail, but get them in so the big geometry fits your space, and then come in and tweak and tweak and tweak as appropriate. Even though it's easy to revise stuff in Revit, to have to come back and fix little things when you've just been making some big changes doesn't make sense. If your whole project sort of works at the same level of detail and gets more and more detail as you go along, as opposed to one part getting highly detailed when other things haven't even been thought out yet. It seems to be a useful way to work. Let's take a 5-minute break and come back at 2:30. We'll start dealing with whatever is next. I wanted to start dealing with door clearances.
Maneuvering clearances at doors.
And although the ADA standards has all those little diagrams of what direction you're coming at, depending on whether the door is swinging in or out, it's hard to keep track of all those. For one thing, the doors aren't all drawn in the same orientation, and you're not always coming in the same orientation. Some are left, right, left swinging, right swinging, in swinging, out swinging. It's hard to put together. So last night, I put together something I've been meaning to do for 10 years, I guess, which is a little graphic to overlay on top of a door that you have in place to see if you've met all the required clearances. So let's just go to component, place component, load family. And for me, it's here on my desktop, class 5. It's the ADA door clearances, no closer family. And it actually behaves like a door in a wall. You just put it right on top of your existing door to see how it works. So I'm going to pick it and say, okay, let's open that. Oh, okay, my mistake. This is a door. It's made like a door, and it was made that way so that it will adjust with the thickness of the wall when it's being placed. So you don't actually load a component, you actually load a door to bring it into the drawing. So cancel this. So actually I go to architecture door load family, and that will import a door into the model, that same one. And we'll do the same thing. Well, these guys are just regular components. So I won't place it right now. I'll hit escape, but it's loaded into this file now, and we'll be here unless we purge it or something. So let's go create a wall. Do a nice one. I'm going to put a regular door in this wall. A regular door, just this, let's say a 36 by 80 standard door. I'll flip it around that way just to see what's going on here. So that little sketch is a door that we will also insert into this wall. It doesn't actually penetrate the wall, it just sits there. The door, use this, and it's only 36 inches wide. I didn't make it so it would accommodate bigger doors because this is what we're all using. And now I can, basically that's inserted into the wall just like a regular door. And it has the same controls, so I can flip it to make it match the door that's there. And then I can just drag it in place so that it overlays the actual door showing the clearances required. So a couple things. Since we're never, a couple either sticking out into the walls, we sort of want to understand what's going on there. But since we're never going to be approaching this door from this direction, we can ignore this rectangle, which is the space we need around the door when we are approaching it from that direction, which would be pull side, handle side, pull side, latch side. So it's the pull side of the door of the wall and the latch side of the door. If we're coming this way, you can zoom and see this arrow indicates this this rectangle, which is a 48 by 60. And we can see that one does not work. If we're coming straight at this wall door here, I need to move this in, click, 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 until we're at least like there. And then move this door, the real door, until it, lines up or is better. It's a nice tool. It's a nice damn tool. And I don't know, actually this goes over here because we're going to the door opening. Okay, so we got a little bit extra clearance there. And we're never approaching the door from this side, so we should be good. I think in the real world, you would probably flip this door that way, flip this that way, and then move it over so you just optimize your space inside the room. These guys can move together. Anyway, I'm very proud of this. And let's make sure of something. If I change that wall to something fatter, it does. It does. It works. It works. It works. So it adjusts on the other side. Just you never know about this stuff. Okay. As we can see from outside or whatever we're in the clear. And because it's it's not part of that door, once you get this one set, you can just erase it or move it over to another one where you happen to need it to be. Yeah, that was really fun to see happen. Let me show you what that family looks like, just as long as we're at it. Edit family. There's the plan view of it. What I found was that the arrows, I couldn't just put them right to touch the line they wanted to be on. They jiggled around some, so I made these a foot and had the line locked in at 5 feet and the door locked in and the arrow locked in at 6 feet. But it worked out. I'm tickled. With the line types available in this door family, I couldn't create like different colored ones, like a red rectangle and a green rectangle and a blue rectangle. But it's clear what's going on. Anyways, so that's that. We can get out of there. We'll get there. You will get there. And I should say this guy is just for the regular door with a latch on it. Like ones in bathrooms that have closers on them, which swing themselves shut. Does this one do that as well? Yeah. There's a little extra 6 inches here and there to deal with, and you can find those back in the ADA standards to know just which one it is. I could do another one door with closer, but there's a couple of permutations on that. So, and I find this takes care of a lot, 90 or 95% of the doors that I put in. And I only did it with 36-inch doors.
Standard wheelchairs are 28 inches wide, and the ADA requires a 32-inch clear opening from the open leaf of the door to the opposite stop. So a 34-inch door will usually be just adequate, but except in extremely tight circumstances, a full 36-inch door is almost always used.
Okay, so that's that. Elevators are going to be easy.
Interior designers are rarely responsible for specifying the size of an elevator, but generally the process would be to select one of the basic orientations from the ADA standards based upon the size of the hoistway and the location of the door. Select a manufacturer like Otis to get actual cab sizes, and then use Revit to place one and adjust its dimensions accordingly.
We just go to architecture, component. Finding them is the tricky part. Place a component, load family, go over to Revit Imperial Library. And this, I think, is in specialty equipment. Specialty equipment, and we got 2 elevators, hydraulic and electric. And as far as I can tell, the dimensions of these behave identically. Hydraulic basically has a piston set into the floor of the elevator shaft, drives the elevator up and down, and electric ones are pulled up by a winch up top somewhere, but it's not our business. We don't care. Let's use electric. Let's see what our options are. Edit type. Well, I think the width and the depth are the size of the shaft, inside sides of the shaft. Cab width and cab depth are the interior measurements of it. That's the only ones that are really, even working with in architectural work, I don't think I've done more than about 10 elevators in 30 or 40 years. It's like I work on little cheap projects. I don't know, maybe that's it. Or they've been there already and we're coming in and doing rehab. But anyway, so you can change all those. And let's say if I change the cab depth, a freight elevator or something we wanted to put in there and make that be 10 feet. Apply. Okay. So gets deeper. Height here refers to the overall height of these rail guides from floor to
just below the roof.
And then I think we had to edit type to get the, this is inserted on level 0. And you can see that the bottom of the guide rails are there on the first floor. Cherokee and I worked over this last night, and I've forgotten everything we did. So that's the height. Was that a type, wasn't it? There. Okay, cab location. So let's take it down to the first floor, to the ground floor. Okay, so there it is. There's its roof or its floor. I'm not sure what is going on there exactly. Usually the structural engineer, somebody's going to be putting that in. We're not going to be. And really, we're just showing basically a rectangle with an X, and that means elevator. Okay, we'll take half an hour to do some plumbing fixtures. Look at them. With a lot of these components that we're putting into buildings, the Kentucky building and plumbing codes are going to tell us what we need and how many, like exits and that kind of stuff, and how wide, how many drinking fountains, for instance. The ADA code will tell us what they need to look like and how they need to behave. So there's always sort of this two-part thing going on. The building code has not, only with respect to like stair heights and ramp runs, has it really accommodated the Americans with Disabilities Act, because it doesn't need to. It would just be overkill, and that makes further possibilities of conflict if they're specifying the same thing, and then one changes, then the other has to change or doesn't, or they fight or something like that. So generally what we need in the building code, and then the ADA to make sure it's accessible. Well, let me just tell you what I went through just working on this Schneider Hall project to see what's involved in figuring out how many toilets and how many drinking fountains we need. And this is something that I've done it for you here for Schneider Hall, first floor, but this is part, and I think Cherokee can attest from her own work on her own house, this becomes part of your self-study as a design professional, certainly to become familiar with the codes and know what's there, and more or less where it is and which book it's in. A lot of it it doesn't become real until you have a real question to answer. And I should point out that here I'm working with the Kentucky Building Code, which is one of the PDFs that I downloaded. That's the whole current version of things. There's also the Kentucky Residential Code, which Cherokee is using for her house, which is more forgiving of stair treads, steeper stairs, narrower stairs, smaller bathrooms, because it's your house, or it's a house that you're going to sell to somebody, as opposed to a public building like a university building where all sorts of people are going to be coming in and out. The residential code also has a lot about actual construction, sizes of joists and that kind of stuff for given spans. Anyway, so for the plumbing fixtures, let me just go through what I did. Determine the number of plumbing fixtures required to meet code for a renovated Schneider Hall lower level. Major renovations almost always require meeting the code. Major renovations almost always require meeting the code requirements for new buildings. So that's what we'll be working with. How hard could this be? So I got the Kentucky Plumbing Code, and all these are available online. You just type Kentucky Plumbing Code download, and there it is, to find out how many people we have to design for. And it's usually like one toilet per X number of people, and what's that number of people? Well, what is that number of people? You have to assume worst case. You have to assume that Schneider Hall we're back in business, COVID is over, every room is full, it's time for a potty break, whoever needs to hit it, hits the bathroom, and we have to be able to accommodate that. So the way that works is, so the plumbing code says, we don't know how many people you got or how to determine that. Go to the Kentucky Building Code to figure it out. Plumbing code refers me to the building code. And that'll happen a lot. They don't want to duplicate information. It's like dimensioning something twice in two different drawings. If it moves, you got to deal with it in some other location. So we go to the Kentucky Building Code. I think I just searched the PDF on the word occupancy until I got to that second table, where it shows that educational classrooms with desks and chairs, you allow 20 net square feet per person. We're not taking into account bathrooms, hallways, storerooms, but we're taking into account all the classroom spaces. That's what the net is about. So 20 net, that doesn't apply to us. We're much more in the shops and other vocational areas in terms of the amount of room that we take up. So I decided to use the 50 square feet net. This is information that you would ultimately attach to the drawings and have them right there, so anybody can see where those numbers are coming from. So I did a quick add up of areas and got about 24,000 square feet for classroom space in this on this floor, and you divide 24,000 by 50, and you get 480 people. Can you imagine being 480 people in class here? So this is when I'm thinking, did I do this right? I think I did, and if I got it wrong, I'll come back and tell you and reissue the spreadsheet. But 480 people. Back in the plumbing code somewhere, it says you can assume, unless it's a girls' dorm, or a boys' locker room, you assume that's half and half. Okay, so that's 240 of each, 240 male, 240 female. Then you go back to the plumbing code to determine how many fixtures per person we're dealing with, or how many people per fixture. And you can see there, it includes, I've sort of cut out a bit of that chart between the titles and us down here, but we're actually considered a business use as far as the plumbing code is concerned, because it's basically all adults able to get there when they need to. So it's actually a business use for schools of higher education, and we get those numbers. And then we go to page 5 and see that if for female water closets for females, we have 1 fixture per 25 people, which is 240 over 25 is 9.6. And you pretty much always round these up. If there's a real space crunch, like in an existing building or something, you can certainly get the code official to say, well, round this one down on this floor, but round it up on the next floor, so we get the same number of fixture units. Same with women. For guys, we split the water closets and the urinals, 5 of each. We got 10 sinks. I know you don't have 10 sinks in the women's room, right? No way. So we're significantly underserved, and that's serving upstairs too. So that's how many we need in number 4, and then number 5 is calculate how many of those need to be accessible. So you go back to the Kentucky Building Code, and it says at least 1 type of each fixture, element, or control or dispenser in each accessible toilet room and bathing room shall be accessible. So that sort of nails that down. A couple of these don't need to be accessible, like a private lavatory off the dean's office does not need to be accessible. It's not open to the public. So that tells us of those 10 female lavatories, of those 10, if they're all in the same room, 1 of them needs to be accessible. But building code doesn't address the number of accessible drinking fountains. So you go to the ADA to see what percentage of drinking fountains need to be accessible. And it's saying basically half. You pretty much always round up to an even number, because most of the time drinking fountains come in that high-low configuration, and you just plug those in. You've got 2 right together in the same plumbing connection and everything. Let me show you how that worksheet works. And this could be adapted for many other uses just by changing the inputs and the formulas. Once you've gone through those couple of pages of stuff, you want to have to go back and keep on retyping things. So what I made here was a spreadsheet where the shaded ones are where we actually enter the numbers from the tables, and then the unshaded ones are where the calculations happen. So if we figure that, let's say this went to 28,000 square feet, and then click out, all those numbers recalculate. So it would be more people, more men, more women, more people to take count of, more fixtures required. So we need 12 of each of these instead of 10 of each of these. If you took out a huge amount of space with your lobby and made this 15,000 square feet instead of 22, then they would all reduce accordingly. So this is here for your use. I think the question here would be, and it was sort of the question I had back on the paper, is do we really have to provide fixtures for 1 fixture for every 50? I'm sorry, 1 person per every 50 square feet. And that's what I will check. But let's say it's 100. We can use a business something, and we come to some much smaller number. So I wanted to keep that all flexible and fluid. And these formulas are dead simple. 150 is just this one divided by that one. The 75 is that one times 50%. Oh, this one equals that one, because that's the same number of women. That one equals that one. These are calculated through just by a couple of simple divisions, and they all keep track of themselves. So let's take this back to 24,050. And let's see, we need to provide, let's just deal with the women's room where we need 10 water closets, one of which is accessible. Just see how that puts together in Revit.
Don't know what our restroom layout will be. Let's just start putting the toilet stalls all in a line.
And these are all in the specialty equipment toilet room component, place component, load family. It's in crank back up here. Specialty equipment, toilet room specialties. So we got standalone grab bars and mirrors and things. Individual toilet itself is still back in plumbing fixtures if we need to place an individual one, but we can just go down and get an accessible toilet stall. Let's use this one, the accessible front with a toilet already in it. How great is that? And these that have bracing and stuff, I don't know, but you can see what we're going to get over here is it won't just place in space. It has to print it against a wall because it needs to be hooked up for plumbing. And it's got the grab bars in it already on the door. So we'll just say, okay. And so I can't place it in space, but I can place it along a wall. And then let's just move it down to have this be the last one, just to start things.
Which is a pretty common arrangement, so its outswing door doesn't get in the way of anything else.
And sort of clicks into place. That was easy. The hard part of this now becomes a true design decision. Do I want an L shape? Do I want two parallel ones? Do I want toilets here and sinks here? And then how's the door getting in? And that's what the Bobrick book is really good about. Because we want to think about, basically when you open the bathroom door, all anybody outside should see is a wall somewhere. Is not any fixtures, not any people unless they're on their way out. So we got that. So let's just say that we're going to do half and half. We're going to do another women's room at the other end of the building, and we're just working on this one now, so I don't have to fill the whole thing up too much. So now we'll go back and get a regular toilet stall component, place component, load family, and here's just a regular toilet stall with a toilet. Overwrite the shared subcomponent family with the toilet stall with the toilet version, blah, blah, blah. I don't know, sure. Well, my guess is, let's just say, I don't know, you should use this one, see what happens. And this is the same kind of a deal where it needs a wall and it will click to the wall. And I'm going to copy that down.
Move.
Delay touch. So what this has given us is the smallest standard stall available. There is one that's not here, which is called an ambulatory accessible. And that's another like 6 inches wider. So somebody can get in there and have a place to hang up their crutches and turn around more conveniently. But for this, we're just doing this. And you can see that this is a little short, but it comes with the bigger version that's as long as this guy. It seems like it got a little wider as well. So we can just copy that from there to there. You thought this was going to be hard. You thought I was saving the hardest part for last. I saved the easiest part for last. So there are those. None of these are yet, have like a changing station or anything in them yet. Maybe that goes on the wall down here, and then whatever. Let's a couple things about the toilets themselves is we're showing all wall-hung toilets, which you'll always have in a commercial facility. They take up less space because you don't need the tank, are far less prone to vandalism. With a residential toilet, you've got that little tube coming out through the wall or the floor or something or other. Don't have any of that. There's no bobbers to mess up and keep running. It's just very straightforward. And they're much easier to clean. You can just mop right underneath them because they don't come down to the floor. So that's all you're going to see here. And they require a strong wall behind them, preferably masonry. So you can really bolt those suckers in there. And a lot of times, and you might even see it in this drawing, you'll have a double wall there where all the plumbing is actually in. This wall goes up, holes are drilled through, the plumbing is installed here, goes into the fixtures, and then this wall is built afterwards. So it's just completely sealed up. And sometimes that will be like the men's room opposite. in which case they put the plumbing in and stub out pipes for the toilets, and then cut the blocks and fit them around and come on through. Let's do individual sinks, see how that works. Component, place component, load family. Sinks aren't here, anything special. Don't think. Those will just be back in plumbing. Oh, changing station. Let's do a changing station. Go get us a sink, at least one of which needs to be handicapped accessible, which are usually longer so the wheelchair can get underneath them and lower. So let's go up to plumbing.
Revit uses the word sinks to refer to ones that are mounted in a countertop or the like. It uses the word lavatories to refer to standalone pedestal or wall-mounted ones and hides them in the MEP folder.
Wall-mounted lavatory, let's just do that. Now, for some reason, Revit thinks okay to like place this on some weird surface that's not vertical. A bunch of these that when they won't seem to click, it's because we're not telling them to place on a vertical plane. But then we can do that. And that could all be one long countertop with separate ones, whatever floats your boat. So this takes care of the walls that we have for plumbing. From now on, we can use regular interior partitions. Let's use this guy. Probably there's probably a stall in here that doesn't have this piece right here, but I'm just going to run this right along next to it for the time being. I don't know what we're going to do here. Let's do a door. Oh, that was my last door. Not yet. Not ready for that yet. And I'm just going to do an opening here. Let's do another door. Now I can do my cool door thing to see if these are going to work for that. DR for door. So I'm going to put it along this wall first. Slide that over. And see that this door, I only approach from this direction. So I need to have all the way down here to be inside there. So we'll pick this and pick the wall and kick up to there. A little extra room. And I need to be clear out to here. So I'll slide that out like that. And now we have, for that door, I've got clear floor space as needed. And that's the only direction we're approaching that one. I don't have to worry about these two arrows. Outside, we don't know what's happening, so let's assume that that's all good. Because I'm approaching from this direction, I'm covered. I'm approaching from this direction, I'm covered. So I'll get rid of that. Actually, I'll say pick a new host and put it here on this door. Having two overlapping is more than my brain can deal with. So we'll do that. Flip it. And realize that as I'm approaching this door from here, I'm good. I think this guy, I think this door swing is really not supposed to overlap that little space. So let's just move that wall down some. Both doors go with it. Now I know I'm clear. We're approaching this door from Generally, we put this over here. Approaching from this direction, I'm good. Approaching from this direction, I'm good. So I think we could use that as a at least initial design for that. I guess, you know, you probably want the sinks to move down a little bit or whatever, but that's how that works. A couple other things let's do with this. I've got a couple other components here. Place component, desktop. I've got a handicap circle. Just to say I've got that, and look, it works in here too, except that it doesn't. Interesting. So that's something else to pay attention to. Okay, and then component architecture component, place component, load family. Anytime you can use the circle, you can also use this shape, which works especially in small bathroom situations where you're sort of having to sort of stick this little prong down between a sink and a toilet or something rather. But those are, as far as the code is concerned, those serve the exact same purpose of making sure that there's room inside the room for a wheelchair to turn completely around without bumping into anything. So, bathroom design. How hard is that? So I will get back to you on those plumbing questions about what our actual numbers are required to see if that changes, because you know it seems to me like 7 or 8 drinking fountains for this floor is just a lot. The thing is that number seems a lot, but if you this room is, let's say it's 30 by 40, 1,200 square feet, divide by 50 is 24 people. And you can get 25 people in here working the way we work. So that seems appropriate. And it comes from that same place where it seemed like a lot of wood had. I know. Well, so that leads me to the question. Okay, is this are my numbers right? And I'll be talking to the guy who knows better than I do. See you guys. Be good.